Um, nice audience. I'm Giacomo Sasso from Queen Mary University. Um, it's quite nice to be here at this conference. I'm a little bit of a fish out of water, I could say, because this is an electronics conference. I'm a roboticist, so I'm kind of related, but I'll try to make it clear that there is an actual clear connection between robotics, actual soft robotics, what I'm gonna talk to about, and electronics. Um, first of all, just kind reminder, you can ask question after my speech, so feel free after the presentation to ask any question. Um, so I'm gonna talk about robotics in a little bit of a different way. So as you can see here in the animation, we see a production line in industry where robots are extensively being used to essentially optimize the manufacturing process in terms of right precision and control at each step, right? And what is a robot? What do we have in mind? Do you actually know what a robot is? So a robot is a machine that can carry out a series of action. And if we integrate this with a computer, it automatically perform functions to replace human effort. I've included as well this question mark, which is what am I? Because we live in a world like nowadays, AI is getting a lot, right? So it's becoming very important to see what's the connection between robots and artificial intelligence. So if we could fully pair a robot with artificial intelligence, we could see him essentially replace himself, or maybe optimize himself, reproduce himself, or maybe organize to take over the world. But a robot, as we are used to think about it, is something that resemble human beings. But why is it so? Why do we say that is similar to humans? That's because we think that humans is perfection, because humans are nature, right? So the chaotic we have all around is actually making something that is like us. But as we can see from essentially the terminology, a robot is something that could actually reassemble human beings. Now, let me introduce you to Bob, which is a normal guy like me. He's from Italy, so he likes pizza as well. Inside of Bob, as we know from school, 80% is made out of water. Isn't it incredible if we think about like 80% of all we are doing, all we are thinking is made out of water, right? And if we go inside Bob, there is a skeleton, which is essentially the only part that is hard, and is making it passive as well, because it's just a structural component. It keeps organs and everything else kept together, but it doesn't have any other function. Instead, all the rest we have inside, which is muscle apparatus, circulatory system, and whatever else, let's say also everything that makes us think, is soft. And comparing weight, if we compare like to a normal Italian guy that eat pizza, 10 kilograms is for the skeleton, and instead 70 kilograms is all the soft part. So I came here to say that we are working on robotics with the wrong assumption, because if we want to make them reassemble human beings, we need to make it soft. Otherwise, we're not doing the right way. So that's why I came here to talk about soft robotics, which is what I've been working on as a PhD student and as a master student. Moreover, I'm going to talk about the interaction and with the external environment and why soft robotics is so important in this field. So, do you know what is a soft robot? And moreover, why do we call it soft? So we call it soft because we just use soft components to make a robot. As a soft components, I could say, for example, liquid, air, right? And robot, I'm saying everything that includes robotics, which is from the control and electronic systems, the energy harvesting, because we need energy to power our robot, right? The active sensing, because we need feedback to understand what's the interaction, how is it going, right? And moreover, the actuation, because we want it to move, we want it to create the interaction. That's the goal. So just to give a brief example of why soft robotics is important, what is the market out there, we're talking about a market that nowadays is $800 million in the world, and is expected to increase to $10,000 million in 2030. Think about the application of having a robot made it soft. For example, in medicals, this is a chamber from Koichi Suzumori, which is a very cool professor from Japan, who developed this chamber, which is essentially made out of a trigonal chamber. And it has rigid components on the length size, which means that when we inflate it with air, it doesn't elongate, instead it bends. And it can create amazing movements and be so small like a coin, right? And if you think about all the application for this, from product lines where you need graspers, where you need grippers to manipulate, for example, very soft materials, for example, food, right? Or other applications such as the medical parts, where we need endoscopes and other things that need a very careful interaction with the human body. That's crucial. Moreover, this is from my friend from MIT, Ellen Roche. She developed this biohybrid sleeve, biohybrid heart. So essentially it's a sleeve that can help your heart pump, right? So it could essentially make your life longer. I included also this cool thing from Clone Robotics, which is a little bit of an out of topic, but it uses soft robotics. Essentially, air is pumped inside of this sort of like contracting sleeves. And with this, they can mimic what the muscles are doing inside their body. And you can see what are the precise movement they can achieve of the entire hand, which is a very complex joint. So, as you can imagine, all the examples I show here are very cool because they have a very nice application in the real world, and they're already existing. So they're already using them for industry, medical applications, and so on. But what's the problem? Why don't we hear a lot about it? Why don't you know about it? That's because we are still facing some hard problems. If you think about this example I showed you now, they are all relying on pressure. And pressure is something that is quite difficult to achieve. You still need a pneumatic system to get that pressure inside of the robot and make it move. So it's very difficult to make it stand alone because we're still relying on that old-fashioned compressor we all know. And also, moreover, we also want to model everything about the robot because we're trying to predict what's the movement. And a soft robot, knowing that it's inflated essentially with air, is not that easy to be modeled. So there are a lot of problems to be tackled. And that's why I'm here a little bit more in the specific to talk about soft robotics, but from the smart materials point of view. So as I said, I'm a soft roboticist, researcher, sorry. I have a biomedical engineering background, and I've been working as part of my PhD on developing electroactive polymers, which are materials that try to get all the function of a robot inside of the material itself. So think about a material that can essentially sense and actuate without the need, for example, of an external huge pump, just for example with an electrical input. So you give an input, you get an actuation, or you get a motion and you get an output as an electrical output. So even more specifically, I've been working on dielectric elastomer actuators that has a fascinating word, which is dielectric. So we are using the capacitive effect to make these transducers, We're also using it for diverse application, for example, actuating, sensing, but also, as I said, generating, because we need power to actuate our robots. So the vision is essentially make a robot fully soft as our body is, except for the structural component. Now, as I said, I was invited by Fabiano to join this conference to give a sort of like out of topic sort of thing. And I was trying to find, Fabiano is one of the organizers, if you don't know it. I was trying to find a connection with the electronics world. And as I said, it's quite simple. It was quite simple for me because I'm using dielectric elastomer actuators, which has the word elastomers, right? But it also has the word dielectric. So at the very base of my project, there is a capacitor. We all know what a capacitor is. A capacitor is essentially an electronic component that can store energy. To make it simpler, you have two electrodes, two conductive components where charges go, they accumulate, and this insulating material, it's slowing the charges flow to the other side. So essentially we are having a charge accumulation and then slowly decreasing on the other side. This is a planar capacitor. So essentially we have the two plates and the insulating layer in between, to make it simple. And the blue part, usually, you know it as hard. But what happens if, well, I mean, I can also show you the pretty known capacitance formula, but what happens if I switch the insulating material with a soft material? So essentially, what I can get a change in capacitance, because what I'm changing is the area to thickness ratio, right? So if I stretch the capacitor, I will get a change in capacitance. And so I will get a change in the output voltage. And if I do the opposite, so I give a different voltage to the soft actuator, soft capacitor, I will get a change in area and so on thickness, because the two plates are attracting each other. So I get an actuator. This is an example to show you essentially what I've been working on and what has been known for actually more than 20 years, but nobody talks about it because, I don't know, we like hard stuff for now. You can see here on the left, this is a side view of a dielectric elastomer actuator. So essentially the blue part, which is the insulating material, it's very thin and it can squish down. And by squishing down, because of volume conservation principle, it also needs to expand. So we have the area expansion. That's a front view, a top view of an actual actuator. The black part is a carbon grease, so essentially it's compliant, it's stretched within the membrane, while the membrane is the blue part, which could be also transparent if we think about it. Now, to give some examples, because I can see some faces saying like, okay, but can we actually use it in the real world? So this guy here, Kevin, I know him from MIT still, he developed a bug-like flying robot that can essentially be and fly like a normal bug thanks to the dielectric elastomer actuators. So with this, it's very important. You saw a very easy configuration because I talked to you about a planar capacitor, but we can make any possible configuration in order to get a lot of different application. For example, they invented also, they invented a rotor, so a motor, which is entirely actuated by the electric elastomer actuators. We developed a laboratory mixer, which mixing components, so the actuating parts are completely soft. And that's quite nice because essentially the mixing container, which is at the center, the little vial there, or just the central top, can move thanks to the actuating motion of these four components. And we can achieve very interesting complex motion dynamics, because essentially the four actuators are soft. So they can actuate also simultaneously, and they don't interfere into each other because they're not joined. Anyway, this work here was published in Nature, and essentially we were trying to see if a sort of like complex dynamic based laboratory mixer could enhance the mixing performances of liquids and could possibly be used, for example, for let's say medical and biology application, because we want to we were investigating essentially if we could feel cells in a different ways all around, right, giving feed and nutriment in different ways. This is also very important because, as I said, we are using capacitors, so we don't have almost, I would say, loss in current, which means that we are not producing any heat out of the device, which means that if we're using this device in a controlled environment, we don't have any heat production outside. So if you think about cells where temperature is massively important, we don't have neither 1 degree of increase in temperature inside of an incubator, and that's astonishing. Just 2 little more examples: VR, AR, augmented reality, Meta, Facebook, Apple. Everyone is working towards trying to keep us inside of a room and feel the world, staying on our chair, right? Or, for example, if we have a girlfriend which is very far away, you can get in touch in a more like physical way. Well, haptics is very important, and as easy as it looks, a bubble light that can inflate can give you the sensation of touch, right? And this device here, which was developed by my supervisor, Professor Federico Carpi from University of Florence, actually. Well, essentially, they developed a bulging mechanism enabled by the electric elastomer actuators, which give you the sensation of touch when actuated, which is crazy because you can feel of touching stuff. I tried it. You can feel of touching stuff just by having these devices on your hand. Lastly, this is a project we've been working on in the last couple of months as a research assistant position. This was also sponsored by ESA, so the European Space Agency. We developed the first 0.5 millimeter thin tunable lens that can beat the focusing performances of a human eye. So essentially, as you know, cameras, they work on shifting the focal point by tuning, and so changing where the lens is related to the sensor. So essentially, as far as the lens can go, you can see what is the focal range you can get with the lens. But your human eye works totally different. Essentially, you have a soft lens inside, which is still soft, right? And it changes its shape thanks to ciliary muscles that stretch this lens and make it change its curvature. That's what we did in a 0.5 millimeter thin lens. And we can, as I said, beat the focusing performance of a human eye. Starting from 4 centimeters, we can focus until infinity. And this is the proof with the big band in the back. So, as I said, I'd like to thank you so much. This is just a quick reminder that robots will think someday. And if they will think, they will say that they love Hardware Pioneer conference, and of course all my sponsors and funding grants. Thank you so much. Thank you.